In the first instant, the Big Bang created the entire universe. But what about the moment before? If time did not yet exist, what does "before" even mean? This question has sparked debate among scientists for decades. Now, new data has been published, revealing clues that could shake our very understanding of the universe's beginning. Today, we will explore the secret hidden within the void, that which may have existed even before the Big Bang. The primordial secret: when the Big Bang unveiled the cosmos. Approximately 13.8 billion years ago, the universe we inhabit began with an unprecedented cataclysm, the Big Bang. This was not a conventional explosion, but a moment when a point smaller than a speck of dust, containing infinite density and energy, suddenly expanded, creating all of space, time, and matter. In an unimaginably brief fraction of a second, the universe inflated by trillions of times. This period, known as cosmic inflation, was like an invisible hand stretching the fabric of space-time, instantly transforming a minuscule singularity into a cosmos expanding faster than the speed of light. This phenomenon does not violate the theory of relativity because it was space itself that expanded, not matter moving through it. Strangely, inflation did not make the universe perfectly uniform. It left behind infinitesimal ripples, quantum fluctuations stretched to cosmic proportions. These tiny variations became the seeds for all cosmic structures we see today, from gas clouds and stars to colossal galaxies. In essence, the entire grand tapestry of the sky began with these minuscule ripples in that primordial moment. After inflation ended, the universe entered a phase of unprecedented chaos. Within the first second, its temperature reached trillions of degrees, hotter than any reactor humans have ever created. Fundamental particles like quarks, electrons, and neutrinos collided, combined, and broke apart continuously. As the temperature dropped, quarks bound together to form protons and neutrons, the first building blocks of atomic nuclei. A few minutes later, a process called primordial nucleosynthesis began. Protons and neutrons combined to form the nuclei of hydrogen, helium, and a small amount of lithium. This was the raw material from which the first stars would form hundreds of millions of years later. At that time, however, true atoms had not yet formed, as electrons were still too energetic to be captured by nuclei. Space was a dense, opaque plasma where light was constantly scattered, unable to travel far. The universe was a murky ocean with no free light. It took 380,000 years after the Big Bang for a new turning point to occur. As the universe expanded and cooled, electrons could finally bind stably with nuclei, forming the first neutral atoms. This event is called the era of recombination. It was at this moment that light was liberated for the first time, free to travel through space. The universe became transparent. That stream of light still echoes today. Scientists call it the cosmic microwave background, CMB, the leftover radiation from the dawn of the universe. Imagine the CMB as the universe's first baby picture, taken when it was just a few 100,000 years old. In 1965, scientists Arno Penzias and Robert Wilson accidentally discovered a faint microwave signal coming from all directions in the sky. At first, they thought it was just noise, but they had actually stumbled upon the oldest trace of the cosmos ever observed. When maps of the CMB were created, they revealed that it was not perfectly smooth, but speckled with tiny temperature variations differing by only a few parts per million. These minuscule asymmetries were the seeds for the entire structure of the universe. Denser spots contracted under gravity, becoming the nuclei of gas clouds, stars, and galaxies. Without these wrinkles in the CMB, our universe today would be nothing but an empty sea of radiation. For decades, scientists have continuously improved their instruments to measure the CMB in greater detail. The European Space Agency's Planck satellite set a record by creating the sharpest map of the CMB. But recently, the Atacama Cosmology Telescope, ACT, in Chile, in collaboration with a research team at Princeton University, has published new data with much higher resolution. They not only recorded temperature differences, but also measured the polarization of the light, the direction of the light wave's oscillations in the early universe. This means we don't just have a static photo of the infant universe. We can also see its heartbeat, how matter moved and oscillated in those first moments. This data provides exquisite details about the distribution of matter and energy when the universe was in its infancy, helping to test and challenge modern cosmological models. From a singularity to a plasma, from an opaque fog to the breakout of light, the entire primordial journey of the universe is preserved in the CMB. But hidden within this picture are surprises. Why do we see colossal structures that defy all predictions? Could they be traces left behind from a universe before the Big Bang? Strange clues, when the universe defies its own rules. If the Big Bang painted the initial picture, the subsequent journey of discovery has led us into a labyrinth of paradoxes. The deeper we look, the more we find strange puzzle pieces that seem to challenge our entire modern understanding. The first thing to baffle scientists is dark matter. Everything we can see, stars, planets, gas, and dust, accounts for only about 5% of the universe's mass. Another 27% is an invisible substance that neither emits nor absorbs light, revealing its presence only through its gravitational pull. Without it, galaxies could not have formed, as the mass of stars and gas alone is not enough to hold them together. Dark matter acts as an invisible scaffold, shaping the entire architecture of the cosmos. Yet, after decades of searching, no one has ever directly detected a particle of dark matter. An even greater mystery is dark energy. In the late 20th century, astronomers made a shocking discovery. The universe is not only expanding, but the rate of expansion is accelerating. Some mysterious force is pushing galaxies apart faster and faster, overpowering gravity. This force is called dark energy. It is estimated to make up about 68% of the universe. This means most of our cosmos is dominated by something whose nature is completely unknown. For years, this simplest hypothesis was that dark energy was a cosmological constant, unchanging in strength. However, recent observations have cast doubt on this. Data from the Dark Energy Survey, after a 3-year survey of millions of galaxies, has offered a bold suggestion: dark energy might be weakening over time. If true, the universe may not expand forever as we thought. One day, the acceleration could slow or even reverse. The mysteries don't stop there. As scientists map the large-scale structure of the universe, they discover colossal formations that exceed all predictions. One of these is the Big Ring, stretching about 1.3 billion light-years across. Nearby is another, even larger structure known as the Giant Arc, which spans an astonishing 3.3 billion light-years. According to the Standard Model, the largest cosmic structures should be no more than about 1.2 billion light-years across. The existence of these cosmic behemoths challenges the cosmological principle, the assumption that the universe is homogeneous and isotropic on large scales. The existence of these massive structures has led many scientists to hypothesize that they could be scars from a previous universe, imprinted onto our own. Some even suggest that mysterious concentric circles observed in the cosmic microwave background could be the legacy of events that occurred before the Big Bang. If true, the Big Bang was not the absolute beginning, but merely a transitional phase in an endless cycle. Bold theories: when the Big Bang is no longer the beginning. The strange clues from dark matter, dark energy, and colossal structures have prompted many scientists to ask a bold question. If the Big Bang was not the absolute beginning, what really happened before it? From this, a series of new theories has emerged, pushing beyond the Standard Model. One of the most famous ideas is the cyclic universe, proposed by physicist Roger Penrose in his conformal cyclic cosmology theory. According to this hypothesis, the Big Bang was not a singular event, but just one phase in an endless cycle of universes, or eons. Each universe, after expanding, eventually becomes cold and empty as matter decays. When nothing remains but radiation, space and time can rescale into the conditions for a new Big Bang. Thus, our Big Bang was simply a rebirth following the end of a previous universe. Penrose even claims to have found evidence of concentric circles in the CMB that could be relics from these lost eons. Another compelling theory is the Big Bounce. In this view, the Big Bang was not a beginning from nothing, but the result of a previous universe collapsing. As the old universe approached a singularity, instead of disappearing, it bounced back, creating a new universe. This idea stems from models of loop quantum gravity, in which space-time is quantized and a singularity is not an endpoint. If correct, the Big Bang was not a starting point, but a transition in a ceaseless cycle. But there are even more radical theories. Some physicists have proposed that the universe did not start with a single explosion, but has undergone a series of smaller, continuous bursts. These cosmic flashes erupt in space, each releasing energy and matter that contribute to the structures we observe. Instead of needing dark energy or dark matter, this theory suggests these distributed explosions could drive expansion and galaxy formation. Additionally, there is the idea of cosmic strings, tiny theoretical defects in space-time left over from the early universe. If they exist, they could act as gravitational seeds, shaping the massive structures we see and explaining why we observe galaxy filaments and walls that exceed predictions. Other models even posit the collision of brains, membranes, in higher dimensional space, with each collision generating a Big Bang-like event. Of course, all these theories remain highly speculative. The observational evidence is not yet sufficient to confirm any single model. But their very existence shows that the Big Bang, while the foundation of modern cosmology, is not the final answer. The fate of the universe, when the future is also a mystery. If the past of the universe is an open question, its future is no less mysterious. Humans have long wondered where the cosmos is heading. Will it expand forever until it becomes a cold, dark void? Or will it collapse back on itself in a fiery end? The answer remains beyond our grasp, but the scientific scenarios are enough to send a shiver down anyone's spine. The first and most widely accepted scenario is the heat death, or Big Freeze. In this vision, dark energy continues to dominate, causing the expansion to accelerate. Galaxies will drift apart until those outside our local group vanish from view, their light no longer able to reach us. Stars will eventually burn out, leaving behind cold remnants like white dwarfs, neutron stars, and black holes. After trillions of years, even black holes will evaporate through Hawking radiation. The ultimate outcome is a cold, empty universe with no free energy to sustain life or any other activity. The second scenario is the Big Crunch. If dark energy weakens or reverses, gravity will eventually win. The universe's expansion will slow, stop, and then reverse. Galaxies, stars, and planets will rush toward each other, temperatures will skyrocket, and the entire cosmos will be crushed into a singularity, returning to a state similar to the one before the Big Bang. The Big Crunch might not be the absolute end, but could be the prelude to a Big Bounce, where from the ashes of a collapsed universe, a new one is born. A third, more terrifying possibility is the Big Rip. In this hypothesis, dark energy grows stronger over time. The repulsive force of expansion would not only separate galaxies, but would tear them apart. Eventually, the Milky Way would be shredded, the solar system destroyed, and even atoms would be ripped asunder as the expansive force overwhelms all other forces. The universe would end in a complete and total disintegration. While these scenarios are based on current measurements, another possibility leans more toward the philosophical. Perhaps the universe has no true end, but merely transitions from one state to another. Just as we suspect the Big Bang was not the beginning, perhaps the end is just the start of another cycle. Faced with this future, humanity seems small. Yet, it is this smallness that ignites our unyielding curiosity. If the universe one day vanishes, the fact that we once asked questions about it, looked up at the sky, and wondered about its ultimate fate is perhaps a victory for the human intellect. From the moment the Big Bang erupted to the distant scenarios of the future, the journey of the universe is still shrouded in shadows no one has touched. We have discovered the cosmic microwave background, identified dark matter and dark energy, and found structures larger than we ever imagined. But these are all just clues, hinting that the cosmic picture is far grander than our current understanding can grasp. Perhaps we will never know for sure what came before the Big Bang or how the universe will end. But this very uncertainty is what makes it so wondrous. As long as humans remain curious and look to the sky with questions, the journey of discovery will never cease. And sometimes, it is the unanswered question that makes the universe more mysterious and captivating than ever before.